As an example of the relationship between a function and its derivatives, we will deduce what the derivative of the function sine of x looks like based on the shape of its graph. So first, let's draw the function sine of x. So we have a y-axis, x-axis, pi over 2, pi, 3 pi over 2, 2 pi. And then the sine function comes up like this, and it comes down, and then it comes under, and it comes back up just like this. So this is y is equal to sine of x. Here's the x-axis. We have 2 pi, pi, 3 pi over 2, and pi over 2. Now, I'm going to line up the graph of the derivative with the x-axis here. So I'm going to create a second graph below it where I line up these points up here. So this is supposed to go straight down. So let's see if I can do that. So this is straight below it. And straight. There we go. So for the graph of the derivative, we'll have pi over 2, pi, 3 pi over 2, and 2 pi, and this will be a graph of dy dx. So this will be the derivative of sine of x. And so we're going to try to get a sense of what this derivative will look like. So first of all, let's just write down the basic rules. So if we have y, so this was that table I showed. So if y is increasing, the derivative is positive. And if y is decreasing, the derivative is negative. So those are the first two. And then if y is concave up, the derivative is increasing. And when the y is concave down, the derivative is decreasing. So these are the relationships between the function and its derivative. So first, let's go through and identify the intervals on which sine of x is increasing and the intervals on which sine of x is decreasing. So first of all, it looks like sine of x is increasing from 0 to pi over 2, right? So we have an increasing arc on that interval, which means the derivative, I'll just put little positive signs here, should be positive from 0 to pi over 2. Next, we note that the function sine of x is decreasing from pi over 2 all the way down to 3 pi over 2, which means that the derivative has to be negative on the same interval. Right? So already, just by looking at where the function is increasing and where it's decreasing, we already know, okay, the derivative is positive here, it has to pass through 0, then it's negative, and it's going to switch to positive again. Because between 3 pi over 2 and 2 pi, the function is increasing once again. So we have an upward trend right here. So the derivative is again positive. So we start off positive, hit 0, negative, hit 0, positive. So the derivative will look something like that. So next, let's look at the concavity of sine of x and identify the exact intervals over which its derivative is increasing and decreasing. So let's see. I guess I'll just use this one. So from 0 to pi, sine of x is concave down. So you can see it looks like a frown. So over this region, from 0 to pi, it's concave down. So that means that from 0 to pi, the function f prime has to be decreasing. So maybe just down here, I'll just denote some down arrows to remind me that the derivative is decreasing from 0 to pi. So we have something that's decreasing because the graph is concave down. And then similarly, from between pi and 2 pi, the function is concave up. So here we have concave up, right? It looks like a smile. So that means that between pi and 2 pi, the derivative is increasing. So we have decreasing, increasing, just like that. So already we know a lot about what the derivative looks like. It's positive and decreasing, negative and decreasing, negative and increasing, and positive and increasing. So it looks something like that. And to add a little bit of an artistic license, we'll add a little bit of a curve to it so it's not exactly just a straight jagged line. And then also we might say, well, where does the derivative start? What's the vertical intercept for the derivative function? So here we would want to look at what the slope of the graph is right there. Now, if you plot sine of x in your graphing calculator or using a computer, and you zoom in, you'll see that if you're very, very close to the origin, it looks like a straight line with slope 1. So the x values will match up perfectly with the y values. So if you just zoom in on the graph, you'll see that sine of x is approximately equal x for small values of x. And of course, you have to be in radian mode. So that means that, well, the slope of the line y is equal to x is 1. So the tangent line is just y is equal to x. And so the value of the derivative at the origin is just 1. So for the derivative, it's going to be positive and decreasing. So we'll start it like that. And then negative and decreasing. And then at pi, it stops decreasing and starts increasing, but it's still negative. And then at 3 pi over 2, it's still increasing, but now it turns positive, so it passes through 0. And then at 2 pi, it stops increasing and presumably starts decreasing again. So this is what the graph of the derivative of sine of x would look like. Now this should look familiar, because this looks very similar to the graph of cosine of x. And if you're guessing that the derivative of sine of x is cosine of x, you'd be absolutely correct. So the derivative of sine of x is equal to cosine of x. So when you see this notation, d by dx, it just means the derivative of whatever's in the brackets. So the derivative of sine of x is equal to cosine of x. And so we basically just saw why that makes perfect sense in terms of the shape of their two graphs. When sine is increasing, cosine is positive. When sine is decreasing, cosine is negative. When sine is concave down, cosine is decreasing, and when sine is concave up, cosine is increasing, and so forth. And it doesn't prove that the derivative of sine of x is equal to cosine x. You can have other things that have this general shape, but as it turns out, it is in fact true. And we'll prove it in the next chapter when we talk about the different derivative rules, and we'll actually use the limit definition to take the limit and show that the derivative of sine of x is cosine of x. One other thing I'd like to point out is at this point, so we have a horizontal tangent here and then down here. So at both of these points, this is where the function f stops increasing and starts decreasing. So the derivative goes from positive to negative. So when you have a horizontal tangent, that corresponds to a 0 of the derivative. Here we have another horizontal tangent, and the derivative again passes through 0. So exactly where these curves level off with 0 slope is exactly when the derivative passes through 0.